Welcome everyone to this Self-Help Africa's Science for Development webinar focusing on global water issues, which we could possibly frame with the phrase water, water everywhere and not a drop to drink. This is part of a series of webinars that showcase student research projects from the 2024 BT Young Scientists. And always we also feature a field scientist from the Self-Help Africa program countries, and today we are going to hear from our office in the Gambia in West Africa. My name is Aaron Towers, and I'm part of the Global Citizenship Education team at Self-Help Africa, and each year we have the pleasure of participating in the Young Scientists and presenting the Science for Development Award. And through this process we come to know many noteworthy student research projects, such as the ones that are featuring today. Always of particular interest to us as a development organization are researches and innovations that are accessible to all, that are climate smart and address social issues faced by rural communities, farming communities, both here, perhaps in Ireland, globally as well, but of particular interest, farming communities in Africa. Communities with which Self-Help Africa works as part of Irish Aid's Programme for Sustainable Development. Today we're focusing on water, and it's a sad fact to think about the reality that still over 2.2 billion people cannot access safe drinking water. And then we reflect that commonly community development is hard fought for and then can quickly be lost or set back due to conflict or natural disaster. So we should reflect now that peace and water are in very short supply in certain parts of the world right now. And we face a big challenge to realize the UN Global Goals 2030, which is a strong part of our work in the Global Citizenship Education team. So let me go to the panel and I'll introduce you to who we have. So we have students joining us from Westmeath and Cavan. You're both very welcome, our groups from the two schools there. We also have our third group from Limerick, and they're going to give us overviews of their research projects into hydroponics and plant stress tolerance. And we're also joined by Self-Help Africa field scientist Mohamed, who's in the Gambia. Mohamed, you're very welcome too, and thanks for making the time to join us. So maybe briefly, as a way of introducing everyone, if I could ask Ellie and Niamh, can you tell us of a memory from the RDS that stands out from being part of the BT Young Scientist? What stands out about that experience?
Probably just like seeing everyone in the opening hall for the first time, seeing everyone that was there. It was just seeing everyone, it was just amazing. So much people in the same situation as us.
And the opening ceremony, it was so good with all the flashing lights, and seeing the president there was actually amazing.
I'm sure that it's the scale of it is quite a lot to take on. Yeah. So excellent, brilliant. And then maybe Laura and Lucy.
Well, I just suppose just seeing how many people were there, I don't think we were expecting that many people. Like seeing all the different projects was just really cool, and meeting so many different people.
And I mean, do you actually have time to see, speak with other students and look at what they've done?
We had about 4 different judges across the days, so we got a lot of time to kind of walk around and go to the different projects and ask a lot of people about theirs and learn about it.
Great, so a positive experience. How about you guys, Patrick, Justin or Ben? Have you got a memory from the RDS experience? No? So hopefully they'll figure that out and they'll come back to us. So let's go and learn about our first project. So if we can go over to Cavan and Ellie and Niamh, and I'll just read out your title of your project. So the title of your project was Navigating the Flood, assessing the effects of water stress priming on plant stress tolerance, which you'll have to explain because that isn't straightforward for me to understand. And your description was to assess the, oh no, you're going to have to help me with this, the Latin, I know it's a kind of cress, isn't it? A mustard plant.
It's garden cress, yeah.
Yeah, and how it responds to excessive water stress, flooding, and to determine whether pre-exposure to water stress enhances their stress tolerance. So there's a whole lot of stress in your project. So tell us a bit of what you're researching here.
So basically, our project is about to see how plants respond to flooding, since we get a lot of rain and water in Ireland. So basically, we found out that they face many abiotic stressors, which are environmental factors or conditions that negatively affect on plant growth. And we picked for our project, for the abiotic stressor flooding, since we do get a lot of rain. So we wanted to see how it affects the plants. So then when the flooding occurs to the plants, we've seen that waterlogging occurs when the soil becomes saturated with water, which then is needed for the plant roots to function properly.
So plants have this thing called epigenetic memory, which helps plants remember things in their genes. And with this, if they get flooded, for example, and then they have time to recover and they get flooded again, they will not respond as much, maybe not even at all.
So for our experiment, we did use the Lepidium sativum, which is just basically garden cress. And we used it because it was basically, it was cheap, it grew fast, so it was just overall handy to use for our project.
So how we did this, so the method, we had two groups, the control group and the group that we'd be stressing. The control group, we grew them out totally like a normal plant you would, but with the groups that we stressed, we grew them out, we flooded them, and another group we grew them out, flooded them, had them recover, and then flooded them again, which the process was 4 days each. And how we measured, we also did this with germinated plants to see how they would react or grow if they were flooded from the beginning. And how we got the results is we basically measured them with to the millimeter, got 10 of them, measured them, did the averages to see the average of them all.
And on our bar chart for the results, we could see that the control group, the average height was pretty high. And then you could see that compared to the stress group, the height did drop a lot since it was stressed by all the flooding. And then when we let the stress group recover, we then stressed them again. And you can see that they did use epigenetic memory and they didn't get damaged as much because they remembered what to do for the next time. So they didn't get as damaged.
So basically, just in conclusion, plants can recover because of the epigenetic memory. So that's just great. But if they get stressed when they're germinating, it can have a long-term damage.
I know this is something I've come across previously, but it's still a very hard one to grasp. You're claiming that plants have a memory. So
yes.
How do you understand that is possible?
I'd say it's because DNA methylation and histone modification, which DNA methylation is like putting a tag on parts in the plant, and they can turn off certain tags if the one part needs more concentration. So like putting a stop if they're focusing on, for example, the leaves, and if because of a flood, they can focus more on the flood and then focus on the less important parts. And histone modification it's like wrapping material, packaging material. So depending how tightly or loosely it is packed, it's how much it's going to get affected.
You think it's proven there with what you did that a plant can learn to respond more quickly to a threat, and therefore be less damaged or less affected?
Yes.
And then did you go beyond that to the idea that learning or reaction could be passed on, through the seeds?
Well, if we did, we haven't really gone any further on this experiment, but if we did, we would do it on crops, because then we would because we actually do live off of crops. We don't really live off of garden cress now, but if we did, we would do the exact same experiment to see if it works on crops, because we actually live off of them now.
Yes, but to be honest, because of transgeneration epigenetic inheritance, the offsprings can develop the memory earlier on.
Great. Well, you really know what you're talking about. How did you come across this area of research?
Okay, so a while ago we were doing our science CBA and it was all about how flooding affects plants, but it didn't really have like much information on it. So we were wondering if there was anything out there that would explain it more, and we couldn't really find much about anything. So we decided to take it on ourselves and give it a challenge and give it a go.
Yeah.
Do you think you'll have time to be involved with the BT Young Scientist again?
Hopefully,
Hopefully.
so, yeah.
And continue with this project, or have you got other ones in mind?
I'd say we would like to go further on more of this side of science, because we really like enjoying learning about plants and stuff in science. So we would like to continue this project on hopefully next year.
Yeah.
Wonderful. Well, thanks a lot. That it's really interesting. It's not something I think we generally give plants credit for, to be able to react to things like that, and then maybe store that knowledge in some form. Hopefully we'll see you at our showcase as well later in the year in Dublin when we bring projects like yours together. Thank you for that presentation.
Thank you.
Thank you.
Let's see now how we're doing with our guys who are in Limerick. Say hello, see if we can hear you.
Yes, we managed to get the mic working.
You got the microphone, brilliant. So I can only see two of you. I have Patrick, Justin, and Ben. Are the three of you there?
Yes, Ben is here, but
Yep.
to get us in.
That's all right. That's all right. Great stuff. So if I can come to you guys just to give us an overview of your project. I'll just give out the title and description as you detailed it for the RDS. And so we've got the applicability of solar distillation in supplying water to third world countries and disaster zones. This will be very interesting, in particular to our scientist and who's joining us from the Gambia. He's going to talk a little bit about the use of solar power and water supplies. And you go on to describe your project as, we intend to create an affordable solar still that can be used by people in disaster zones and developing nations to clean water. How can you use solar power to clean water?
We'll start off with the model itself. You'll be able to see it too well now.
Our solar still is basically a box in a box to keep the heat in. It kind of uses a thermos effect. And then in the inner box, there is two sections, a dirty and clean water section. You would put your dirty water in, and using the sun, it'll heat it up, evaporate, condensate, and then you'll have your clean water come through then on the clean side, and it's basically just a passive way of filtering water.
And when you say dirty water, what do you mean by putting in water that is dirty?
Any form of contaminant.
Unfiltered water with bacteria, dirt.
Explain to us how you became aware of this issue and this way of dealing with dirty water.
Solar distillation has been around years. It's a very common form of purifying water for campers, people who go out backpacking in the mountains. I remember when I was younger, I had loads of survival plans by me. And in one of those, ground still is a very ineffective form of solar still. It works through digging a hole in wet dirt and then putting a clear plastic tarp over it, which would then evaporate and condensate the water. I found that idea incredible, that you could purify water using nothing but the sunlight. So we took that, we researched the fact that there are many other types of solar cells, and then with that knowledge, we put together our own version that could then be applied to developing countries to help solve their own water crisis. The main selling point of designed it in a way that could be replicated. We would give the information so that they could then create their own solar cell.
Unfortunately, we're having a little bit of problems with your microphone. It's not very clear, but I think we're getting a gist of what you're saying. Great approach to an issue. The core reason or sort of process that you're following is that it has to be accessible and affordable to people that are unable to access safe drinking water. So as cheap as possible and using as simple materials Did you try a few different approaches as you went through it, and what did you come up with a certain material or a way that is also affordable but is more effective?
We originally wanted to use metal, but then that's not really accessible in some parts of Africa. So we decided then to switch to wood. And we used a thermos effect instead of using standard insulation, which would be the standard practice for making a single photo. The most effective without jeopardizing the fact that it has to keep in water and keep in heat at the same time. We try to make it just as cheap and affordable as possible.
I missed a little bit. Do you think some of the materials, like you mentioned wood, it could be recycled materials that are waste materials that are there and could be reconstituted?
Absolutely.
Well, all the materials that we used to make our model was all recycled, all scrap wood, scrap plastic sheet. It's 100% made of recycled materials.
Well, there you go. Brilliant. Obviously, you were holding up a small enough box. Can it be scaled up, or how much water can you clean in a box that you were using as a demonstration there?
It really depends on how much you put in. I don't remember off the top of my head for max efficiency, but I'm sure we have it wrote down somewhere.
The ideal size of our solar cell would be 1 meter by 1 meter. What we have here is a third of the size of that. It's a model. It still functions, but it produces less than the required amount of water for one person in one day. Now, because solar cells have been around so long, we centered our project more around the plans which we could use to apply these solar cells into developing countries. So we wrote a good few essays and did a lot of research on countries where this could be applied and how. We did research and wrote essays on where, like in these countries, and how we'd apply it to different regions. Then we put work into financing it. We put together a finance plan, which is also detailed in a different essay, and we put together a demonstration website.
Wow. Well, brilliant. You really went much further than just the sort of the science element to it. So fair play, brilliant. And do you think you're going to continue with bringing? Or it sounds like you're almost ready to go to market.
Ideally, it would never go to market. I suppose that's the project that we'd it'd be an exchange of information rather than the product itself. But we have taken the project a good bit further. We're currently finalists in the YEAs. We took this to BT Young Scientist, and from there we expanded the project to, which ended us being invited to the YEAs and this competition itself, which was brilliant. We'd like to take the project as far as we can. Anyone that's interested, we'll bring it to them.
Well, I look forward to, hopefully, if you can make it, that you can make it up to Dublin in September or October to our event, and I get to see the actual unit. So thanks for all that. Sorry for the technical issues. Thank you very much. So if I can move on to our final school group, and we have Laura and Lucy from Moate Community School representing their project, and their colleague Niamh couldn't make it, so that would be the three of them. We have Laura and Lucy with us, and they had a project, or they have a project called Optimising Hydroponics for Use in Developing Countries, and described it as the project aims to develop a closed hydroponic system to improve the yield and nutrient content of crops in developing countries. So what is hydroponics, and what is a closed hydroponic system?
Hydroponics is basically you can grow plants without using soil. So we thought that this was a really cool thing and we wanted to look into it. A closed hydroponic system. So at the end of our project, after all our research, so it's basically, we made a miniature greenhouse with our system inside of it. So it provides the place for the plants to grow hydroponically.
Yeah, go ahead. Tell us a bit more about what you did.
Well, to start off, we had to look, obviously we're not using soil, so we need to find different materials to use. So we looked at various materials. for different jobs that soil does.
Our focus country was Ethiopia. So we looked at different materials available. Our starting material was sheep wool. There's over 40 million native sheep in Ethiopia. Obviously, it's really hot over there, so it's a very easy access to sheep wool. And then we had flax. Flax is really cheap and it's a really common thing found over there. And then next we had shredded jeans. There's a lot of landfills that take up room in Ethiopia, and obviously like denim, any sort of like denim with jeans or whatever is common in them. So we use that as well. In natural soil, there's three things that make it up: clay, sand, and silt. So we needed to find a replacement for each one of those. We did loads of experiments to find out which was kind of the best at which job. So sheep wool was found to be really good at absorbency. So we use that at the bottom of our hydroponic system, and that's in replacement of soil. And then next was flax, which was the middle layer. This was to replace the sand in soil, and it replaced it as it performed really well in our drainage experiment. And then on top, we used shredded jeans. That was to replace the silt in soil, and it was on the top to because it performed really well in our germination.
Who'd have thought it, they use genes in such a way. People might be wondering why go to all this bother when you can just plant things in the ground. Why can't you just grow things in the soil in Ethiopia?
Nearly all of these are waste materials. So like such things as shredded jeans, like they're just going to landfill. So this is another way to recycle. So we're using them as a completely different way that no one thought we could, which is to grow plants. Recently, Ethiopia has experienced a lot of drought. So a lot of the soil in the crop areas, they're made mostly of clay. So the other silt and sand isn't provided a lot. So it's not the best conditions for crops to be growing. We're recycling materials, which is sustainable for the earth. And we're also helping out the drought that's happening in Ethiopia. So these are our bar charts for our experiments. So we did absorbency, drainage, germination, and water retention, which helped us to figure out our three final materials, which was shredded jeans, flax, and sheep wool. Obviously, plants need sunlight and water to grow. So we said soil also provides natural nutrients for the plants when growing. So as we're no longer growing them in soil, we needed to find a way to implement them into the plants. We wanted to find an easy way, so not make extra work for yourself. So we said, if you're like boiling carrots or potatoes at home, what would that water left over do for the plants? So we looked at the water after boiling potato in water, after boiling banana skins, carrots, and cabbage. And we also used chickpea juice, and chickpeas are common being grown in Ethiopia. So we looked at the different concentrations of nitrate, phosphates, and the pH level. So in the end, we saw that potato water was the best for the plants. Sorry, it's actually banana water that performed the best. It had a good phosphate and nitrate concentration to balance out the nutrients that a plant would need. And it also was in the optimum pH range for a plant, which lies between 6.5 and 7.5. So we did trials on growing cress seeds with all of the wastewaters, and banana pellets performed over the top compared to every other experiment. As you can see in the picture below, the length of the roots and the shoots were performed way better.
Am I right in thinking when you're talking about this kind of medium of growing that you're also using a lot less water? It's very carefully controlled irrigation, and then you're using wastewater, which actually has more nutrient value in it anyway.
So our materials like sheep, it kind of works as a recycling system in our pot. So it can be held in the sheep wool, and when it gets hotter, it will evaporate back up to the shredded jeans. Like it's a cycle of water. If it's not used, it will be reused, and not wasting any water. Like we're minimizing the water that we waste when we're using it to grow plants.
Here we have our hydroponic system, a bottle from a water cooler that was like donated to us. We put several holes in it to fit our like plant pots. So the plant pots are actually the bottom of recycled plastic water bottles. We put them in each hole and then obviously we put our materials in it. We have like an orange hose going through. The hose connects to the top of the bottle, and then each hose goes to a different pot, and it goes in the end. So when we want to water the plants, like different plants kind of need different waters, so we can put them through the hose, and then they go through the hose and then go into the bottom. Since the water is going into the bottom of the plant instead of the top, it's a lot more beneficial to the plant.
It looks a really interesting, innovative approach, and using a lot of recycled plastic bottles and in a very clever way. Do you see this as something that a family would utilize as a different way of having a garden, like a vegetable garden?
Yeah, like this is pretty simple. I suppose we were looking at vertical growing as well in our project. So like that was just a certain way that we did it. Like at home you can just do it in plant pots, put your materials in and start growing from there. This box that it's in, it's like a miniature greenhouse that we built just to try out growing the plants. So that helps wasting water as well, as the condensation will go on the windows and come back down, and then you can rewater that into the plants.
Very good. And you have some conclusions or recommendations?
We obviously have a lot further to come with this project, and then we plan to do BT again in DY and maybe take it a bit further and see what we can do with it. We would recommend to examine the crop yield after a complete growing session in our hydroponic system, being fertilized on our wastewater cooking fluid, as well as being supported with our banana skin pellets. So for example, we got banana peels. We kind of blended them into a bit of a powder. We mixed it with hydrochloric acid and sodium alginate. That mixed into a bit of a pellet. And then when we put the pellets on the fake soil, it provided even more nutrients to the plants.
Wonderful, wonderful. Yeah, no, I mean, really interesting approach to hydroponics, because often you see it showcased as quite a high-tech way of growing, and with a very specific type of kit that you have to buy, and a growing medium which can be expensive. To approach it in the way you have, everything is waste materials or available around you, and utilizing nutrient-rich wastewater and things like banana peel, and even turning it into a pellet. That sounds really interesting, especially if it could actually be some form of income generation in the area for someone to produce something from a waste product and turn it into something valuable. That's always a very important part of the work of Self-Help Africa, is income generation. Thanks a lot for that. There's a lot in that project. It's really great. We'll go over to our very patient guest from the Gambia, our scientist, Mohamed Lahai. Thanks very much for joining us. And Mohamed is our project officer in the Gambia for the WASH program, which he'll explain a little bit, is the acronym for water, sanitation and hygiene. He's going to explain one particular program that they're involved in now that is very relevant to our discussion around water and the access of clean water. So please, Mohamed, we'll show you your slides. Tell us what you're up to in West Africa.
Thank you all for your beautiful presentation, all the students, and thank you, Ara. In the Gambia, we started WASH not long ago. I think this is our second year into the WASH program. We had funds from Waterloo Foundation to actually pilot rehabilitation of boreholes, because in the Gambia, 70% of the boreholes that were functional are no more functional. So we have boreholes, but they are no more functional. Like after 2-3 months, they have faults again. So what the project actually looked at is to rehabilitate those boreholes that are non-functional.
Maybe if we go to the next slide, if you can just explain to us what a borehole is, because it's not something most people here would be familiar with.
Yeah, this is a solar-powered borehole. It's powered with solar with a pump inside the drill hole, which where the water is pumped into the tower, the one you could see, the tanks of the tower. The solar generates the electricity, and the pump inside supplies the water to the tank. Then this tank has an outlet that supplies the water to the community. From the picture we are saying, that's two 2,000 liter tanks. That is two double 1,000 liter tanks. That is 4,000 liter tanks. This is a small community of 40 households. This community has been struggling with access to clean drinking water. They had a borehole actually before, but the water was not sufficient for the community, and the panels and the pump inside was also broken down for some time. So before we intervened in this community used to have used to get water from an open well. So when we intervened, we rehabilitated their boreholes. Now this community has access to clean, sustainable drinking water, because what we put in is not just access to clean water, but also we make sure that we have put in mechanism to make sure that the borehole is functional and sustainable for a period of time. Let it not just be like we rehabilitate a borehole. After 1 or 2 months, it breaks down. Then the community have to go back to the same system they were getting water from, which is actually not safe and not sustainable for them to continue drinking from the well water, because it's not clean. It's not a clean source of drinking water, because it has a lot of contaminants and which can affect their health. So this project doesn't only focus on rehabilitation of this um, borehole, because just providing water is not the solution, but also making sure that you provide safe and clean drinking water for this community. The other aspect that we look at, that is the quality of water we supply to this community. So for our project, we fit in all these boreholes that we are working. The four boreholes we rehabilitated. We had these options that we tried. We trialed for the last 6 months. We trialed the plastic filters, and we also trialed the inline chlorinators. So for the inline chlorinators, this is this one. If you could see the white pipe on top, yes, the white pipe on top, it's an inline chlorinator. It's where you put the chlorine, which supplies the water of the pipe that goes in the community. Then it's where this chlorine has been fitted to actually chlorinize the water, because we found out that chlorine is one of the best ways of making sure that you purify the water for the communities. It has an opening, and where you put your chlorine taps. Chlorine taps are it's fitted for the size of a chlorine tap. So if you could see, so if you put a chlorine tap into this, it has a regulator which regulates the amount of chlorine that suitable for consumption, or it's acceptable at global standard. So you regulate the chlorine to that standard, then the water is then supplied to the community. There's also the we have another option that we trial, plastic filters, or sometimes called the candle filters. So just like what Patrick and Justin and Ben were explaining, it's similar, but ours is more. Patrick, Justin, and Ben actually, because I wanted to ask them with regards to what about the chemical components of, because water is not just the biological component. If the chemical component surpasses, it also affects the health of the individuals consuming this water. So this inside these buckets we fit in chlorine tubes. They have filters inside, which if you put a dirty water or unchlorinated water, These tubes will filter the water, which will be dropped down into the next bucket. If you could see, there is another bucket. But on this bucket, there is a tap fitted on all of this bucket. So instead of putting a cup, so this was made in the Gambia by some of our local producers, but the tube inside, the chlorine tube inside was made in Senegal. In the Gambia here, most people dip in the cup inside the water, which they don't actually take care of these cups. Oh, these cups are exposed outside. So what we did was we actually do sensitization and also wash refresher training for this community. When we brought this bucket, we actually found that it actually improved the water quality of these communities actually improved, because instead of them using cups to drink water or using their local jars or using their local buckets which are not covered or are not cleaned. So when we introduced, we actually found out that the communities have health have actually improved because of the filters inside these buckets that is used to clean water.
Always, it's very important to inform and to have discussions with communities as when any kind of change or innovation is being trialed, that people have to be involved in understanding what the problems might be and how things can be improved. The importance of keeping water sources covered and then not contaminating them when you're collecting the water.
In these communities, we actually first did water quality testing for these communities where we actually rehabilitated pools and found out that the chemical components of the water are actually okay, but the biological component, that is the E. coli and the total coliform, most of these waters were affected with E. coli and total coliform, which actually affects their health, because if you drink a lot of coliform, E. coli and total coliform, it might actually result to you having diarrhea, and which in these rural areas they don't actually have very good medical system, so which actually can result to death and other diseases that affect children and even adults in these communities. So when we did the water quality testing, we found out that it's not just providing water to these people. You need to provide clean, sustainable drinking water to these people, because those days they were getting water from the open wells, and even when they had boreholes that were functional, they didn't have any other system or any mechanism in which they clean this water. So even if the underground water is clean and is pumped into the system, when it goes to their households, the storage facilities where they put these waters might be contaminated. So that's why we provided them with this, and also the inline chlorinators, where the water is treated from source, goes into the pipe system, and this serve as a storage where they put the water and they can drink from the tap instead of now using cups to dip. Everyone come in with a dirty cup just to dip in and drink water. So thank you very much. Yeah.
Thank you, Mohammed. That was brilliant. I think it's really interesting place to conclude. Really, it does come down to awareness and education. And here we are with these great student projects and schools watching in. That's like, even that you could do all these steps of providing clean water right up into the source, but if people aren't involved and empowered with knowledge, the contamination can happen right at the very end. And if people are not given the awareness and the ability to test the things at source, be that dirty water or what in whatever else, they don't have the power to keep themselves well and their family and provide for their community. Always that important element that everybody is involved and understands what these innovations are for and how best to use them. Otherwise, it doesn't work. And so that's really brilliant example of all the way down the line to the community level that everybody is involved and informed. So I just conclude the webinar there, and I thank all our panelists, Mohammed in the Gambia and our 3 school groups. Thank you for making time for us and your presentations. And it's really inspiring to hear that the projects aren't at an end. They are being continued, and that you're inspired to get involved with the Young Scientist again or other such events. So best of luck with that. And hopefully what you have presented today will be inspiring to the students that are thinking of going for such things like the BT Young Scientist next year, and teachers as well, gives them some things to think about. So thank you very much for attending and taking part. And like I say, we hope that you are able to join us in September at our showcase.